Dual combustion cycles are in a way a combination of the Otto cycle and the diesel cycle. They can be referred to as mixed cycle, Trinkler cycle, Seiliger cycle, or Sabath cycle. We had already made a distinction between the spark ignition engines, Otto cycle, and the compression ignition engines in the previous two main lectures, so make sure you have watched and studied those two 10-minute lectures before watching this. Because there is no spark involved in the dual or mixed cycles, they are usually categorized as a more modern variation of a diesel engine. Fuel is injected into the combustion chamber much sooner in a dual cycle than in a regular diesel cycle. For this reason, since fuel starts to ignite late in the compression stroke, part of the combustion happens almost at constant volume. Before the piston reaches TDC, fuel starts to come in, and for a short period of time it ignites while the piston is almost still. What this means is that the heat addition process is split into two stages. One that can be assumed to happen at constant volume, and one at constant pressure once the piston does start moving considerably. A PV diagram would look just like either an Otto cycle or a diesel cycle between 4, 1, and 2, which haven't changed at all, with the difference here being a heat addition process at constant volume, similar to the Otto cycle between 2 and X, and a heat addition process at constant pressure, similar to the diesel cycle between X and 3. The implications of these changes should be apparent if your Otto and diesel cycle bases are strong. The specific volume at 2 and X are the same, just like the pressure at X and 3 are the same. The heat in from 2 to X can be calculated as the change in internal energy, and the heat in from X to 3 can be calculated as the change in enthalpy. The total heat in would be the sum of these two. In the case where we use constant specific heats, we would write CV times Tx minus T2 for the isochoric heat in, and Cp times T3 minus Tx for the isobaric heat in. Besides the compression ratio and the cutoff ratio explained during the diesel cycle's 10-minute lecture, we typically need to know the pressure ratio as well. This pressure ratio is that between the pressure at 2 and X. A TS diagram doesn't add much information to what we need for a dual cycle, but we can definitely draw one with isochoric heat addition between 2 and X and an isobaric heat addition between X and 3. Let's look at a quick example where we use what we learned here, and if you want to check out other examples on this topic, make sure to check out the links in the description below. A dual combustion cycle has a compression ratio of 15 and a cutoff ratio of 1.2. The pressure ratio during the constant volume heat addition process is 1.6. Using constant specific heats at 300 Kelvin, determine the thermal efficiency when air enters at 90 kPa and 290 Kelvin at the beginning of the compression. As usual, try pausing here for a minute and solve this yourself before watching the solution up next. The thermal efficiency definition has not changed with respect to other gas cycles. Therefore, we need the heat out and the heat in. Let's begin with the heat out. The heat out still happens at constant volume like in Otto or diesel cycles. And since we're using constant specific heats, this is C sub V times the temperature difference. Since we have an isentropic process between 3 and 4, and we're using constant specific heats, we are going to need the volume ratio V3 over V4. V3 can be found using the cutoff ratio and the volume at X. We don't have the volume at X, but we know it's the same as the volume at 2. And V2 is V1 over the compression ratio. V4 is just V1, and since we have P1 and T1, V1 can be found with the ideal gas equation. Now for T3, we can use ideal gas between X and 3. We already have the volumes, but we need the temperature at X. And again, with ideal gas, we can find Tx in terms of T2 and the pressures. Since P3 is Px, this fraction is the pressure ratio. And finally, between 1 and 2, we have an isentropic process too, so T2 can be written in terms of T1 and the V ratio. We look up K and CV for air at 300 Kelvin, like the problem asked, and we substitute all of the numbers that we can calculate to find the total heat out Q out. And now for Q in. We already saw that this is the heat coming in between 2 and X, plus the heat coming in between X and 3. One of them is isochoric, meaning that we use CV, and the other one is isobaric, meaning we use Cp. We look up the Cp value for air at 300 Kelvin, and we substitute all the now known values to find Qn. And with that, we substitute the heats to find the efficiency. If you want to check out other diesel cycle or dual cycle examples, make sure to check out the links in the description below. You'll find the links to the other lectures of the thermo course as well as other engineering courses playlists. Thanks for watching.